Okay, for section 4. First up, before I get started, let me apologize for being gone. I'm going to try to get through, well, we'll get through this today. All the subs show this since today is Friday. I'm actually going to push the quiz. I will have written this on the backboard as well, but I'm going to push the quiz till Tuesday so you guys have a chance to ask questions on Monday. And we'll also have that work day on Monday. So, just to get through this, sum and difference formulas. Okay, so now we're going to start adding some of the other formulas into the mix. Okay, this stuff will not be on the quiz on Tuesday. Sum and difference formulas are straight out of the front of your book. The idea is if you're adding two angles together, you can simplify things out, or if you're subtracting them, same thing. So if you know angles U and V combined together give you some other angle, then you can use the fact that U and V are whatever they are to find that. Okay? Same thing, there's sine and cosine and tangent versions of these. Sine and cosine ones aren't too bad for the most part. Sine is just sine times cosine plus cosine times sine, just switching the angles. If it's plus, it's plus. If it's minus, it's minus. Cosine does the opposite though. When it's plus, it's minus between them. When it's minus, it's plus between them. And you're just going to do cosine of the first angle to cosine of the second, and then sine of the first angle, sine of the second. Tangent's a little more convoluted. Some people like to actually just split that up and do sine and cosine separately for it, because you could do sine of u plus v over cosine of u plus v. Gives you one less to remember, but it takes a little more time. But we'll take a look at them. If I want to find the exact value of cosine of pi over 12, so the idea is I want to split the pi over 12, which I don't know naturally, into something I do know. So pi over 12, this is where fractions and knowledge of them helps a lot. So for pi over 12, I'm going to think of that as 1/12. Now in the first quadrant, I know pi over 3, pi over 6, and pi over 4. If I want to get 1/12, I can actually use these. I'm going to take the pi over 3, because pi over 3 is actually 4 pi over 12, and subtract from that pi over 4, because that's 3 pi over 12. 4 pi over 12 minus 3 pi over 12 gives you 1 pi over 12. So the idea is, even though I don't know pi over 12, I can separate it out into two that I do know. So once I have that, I'm going to use that law of cosine, just got done teaching a FS&T lesson on law of cosines. I can use those sum and difference formulas for cosine. Now, I'm subtracting these two things, so I'm going to do cosine of those two minus. That means I'm going to do cosine of the first times cosine of the second minus sine of the first times sine of the second. Okay? Now these will be, since they want exact answers, they're going to want these from the unit circle. You're not going to be able to just type these into the calculator individually and give me the decimal. It will be counted wrong. Cosine of pi over 3, if I think about that one, that's up here, so it's closer this way. That's going to be 1/2. Cosine of pi over 4, square root of 2 over 2. Minus sine of pi over 3, well, if that was 1/2, this is going to be square root of 3 over 2. And sine of pi over 4 is the same as cosine of pi over 4, which is square root of 2 over 2. So when I multiply these out, that's going to give me square root of 2 over 4 on the left, minus square root of 3 times square root of 2 is square root of 6 over 4 on the right. So that simplifies out to just be square root of 2 minus square root of 6. I can't combine those together, all over 4. Okay. Now this is where I do the pause, because what did we do wrong? For cosine, if it is minus here, when you go to the different form, it's plus. Good thing is it's a fairly easy fix, because I still can't combine anything together, but that should be a plus sign. The other reason I knew that was wrong was because square root of 2 minus square root of 6, square root of 6 is bigger, that would have given me a negative number. Cosine of pi over 12 is in the first quadrant, it shouldn't be negative. Okay, so you can also do it with degrees. Find the exact value of sine of 75 degrees. 75 degrees I can get by taking, well, the same two we just did, except adding them. I can take the sine of 45 plus 30. That'll give me sine of 75. So when I do the sine for sum and difference rules, well, this is the sum. So I'm going to do sine of the first times cosine of the second plus sine of the second times cosine of the first. If I actually look back at the formulas, I think they flip these two, but because I'm multiplying, the order doesn't matter on each side of this symbol. So plugging it in, sine of 45 square root 2 over 2. Cosine of 30 this time is square root of 3 over 2. Plus sine of 30 is 1/2. Cosine of 45 is again square root of 2 over 2. So you're going to get the square root of 6 over 4 plus square root of 2 over 2 over 4, sorry, which again is going to be square root of 6 plus square root of 2 over 4. Which, if you stop and think about it for a second, this is sine, that was cosine. You get the same answers for both of these. Well, if you think about it though, sine is the vertical from the x-axis, right? So that's going to be equivalent to 15 degrees, which is what pi over 12 is. 15 degrees away from the y-axis when you're up 15 degrees. Or for sine, 75 degrees is just off of the y-axis, so how far up you are from the x, that 15 degrees off of the y. Okay. Let's take a look at the next one. Find the exact value of cosine of u plus v. Given sine of u is 7/25, cosine of v is -4/5. They also give you quadrants. So the idea is if I want to do u plus v, well, I'm going to jump straight to that formula. Well, that's going to be cosine of u times cosine of v. Because this is plus, it's going to be minus sine of u times sine of v. And I can plug in some of these now. I know the cosine of v is -4/5. I know the sine of u is 7/25. The problem is here, I need to find these values. Now in order to do that, I need to think about what kind of triangles I'm dealing with here. Cosine of v is -4/5. Well then, cosine or sine of v, I should say. If I actually draw this triangle, we're between pi over 2 and pi, so we're in this quadrant. -4/5 means I'm going to go over here somewhere, where I have adjacent over hypotenuse is 4/5. The other side then has to be 3. Now if you want to, you can also use the Pythagorean identities. The sine squared plus cosine squared equals 1. Either way works. But I end up getting for sine of v 3/5, and since we're in the second quadrant, that has to be positive. Do the same thing with 7 and 25, except for now we're in the first quadrant. 7/25 is a fairly small number, so I'm going to go about up here. So that's going to be 7 on the opposite side, 25 on the hypotenuse. This side, if you plug into the calculator or if you're comfortable with it, gives you 24. It's a Pythagorean triple. So since we're in the first quadrant, cosine is going to be positive, adjacent over hypotenuse. Then multiply them together. 4 times 24 is going to give me -96. 5 times 25 is 125. That's going to be minus 21 over again 125. -96 minus 21 is going to go even more negative, so I end up with a -117 over 125. That one's still not too bad. It's just one extra step in having to find those ones you don't know. This one is a little more work. But it works back to the same stuff we were doing previously in section 2, I think. Sine of the arctangent of 1 plus arccosine of x. Or maybe I'm thinking last chapter. It's running together. It's about 5:30 right now. So, if I want to write that as an algebraic expression, I need to replace the arctangent of 1 with whatever the angle is in this case. Okay? So the angle for this, I'm going to set up. Now, if that's 1, that means the ratio opposite to adjacent is 1, which means the hypotenuse, if I take those and square them, well, they're still 1, add them up, you get 2, square root it, you get the square root of 2. The other way you can think about arctangent of 1, that pretty much has to be 45 degrees. Okay, you don't have to do it that way, but that's fine. Arccosine of x, for that one. Arccosine of x is going to be, I'm going to put it over 1 again, adjacent to the angle is x, hypotenuse is 1. That means your opposite side is going to be the square root of 1 squared minus x squared. So So now I can actually set sine of the inverse tangent of 1 times cosine of the other one, which is arc cosine of x. Now since that's plus and we're doing sine, it's going to be plus again. Now sine of the second one, sine of the arc cosine of x, should be another c in there, times cosine of the arc tangent of x. Or 1, sorry. Okay? So now that I have the two triangles, I'm going to use those. Now, sine of the arc tangent of 1, well, I'm going to go up to this triangle, and I'm going to do sine for this angle. Well, that's going to be opposite of our hypotenuse, so that's going to be 1 over the square root of 2. And I'll mess with that later. Cosine of the arc cosine of x, the nice thing there, that one's very easy. It's just x. Plus sine of the arc cosine of x. Now I'm going to go up here and do sine. So that's going to be the opposite over hypotenuse. Well, that's just going to give me the square root of 1 minus x squared. And lastly, cosine of the arctangent of 1. Well, that's going to go over here. Cosine is going to be 1 over the square root of 2 again. Okay? So when I multiply these out, that's going to give me x over the square root of 2 plus square root of 1 minus x squared over the square root of 2. So then I can combine those together into x plus the square root of 1 minus x squared divided by the square root of 2. And I would actually just leave it that way. You could rationalize the denominator, but it's going to be really ugly no matter what. And this process more so is important up above rather than trying to simplify the denominator in this case. That's about as bad as they honestly get. We do have some other examples I want to go through, but let's see. Yeah, we'll just keep going. This one is asking you to prove the cofunction identity. So this is proving that a specific cofunction identity. I honestly don't remember if it's one in the front of the book or not. It doesn't really matter because I have sine of two things subtracted. So I'm going to use the sum and difference formulas for that, the difference of sine. So I'm going to take sine of the first, it's times cosine of the second. Now the negative does not go with the pi over 2. You could put it there if you like and change this to a sum problem instead of a difference problem, but it's easier just to use, since this is minus for the sine, and then do sine of the second times cosine of the first. Now when I do that, what's going to happen here, and this happens a lot when you start dealing with 90-degree angles or multiples thereof, cosine of pi over 2 is 0. So I have 0 times the sine of x, well, obviously that's going to go away, minus sine of pi over 2 is just 1 times cosine of x. Well, that equals negative cosine x. So it's not too bad. It looks ugly at first, but it's not that much. If I want to simplify an expression like this, it's actually the same as the proof problem. They're just not showing you the other side of it. So I'm going to go through the same type of process. I'm going to do sine of the first times cosine of the second minus sine of the second times cosine of the first. So when I do that, sine of 3 pi over 2 is negative 1 minus sine of theta times cosine of 3 pi over 2 is again 0. So those go away. You're left with negative cosine again. Now tangent, this is where you probably have to look back at the formula in front of your book, and that's fine, because this one's a little bit harder. I'm subtracting here. So this one is going to be tangent of the first minus tangent of the second on top, divided by 1 plus tangent of the first times tangent of the second on the bottom. Okay. If this was plus, then the only difference would be you'd have positive on top, negative on the bottom. Okay. Then go from there to simplify. I have tangent of theta minus tangent of pi over 4. Pi over 4, 45 degrees, is 1. Divided by 1 plus, again, that's going to be tangent of pi over 4, so that's going to be 1 plus tangent of theta times 1, doesn't matter, and you get that. It's not going to go any further. Okay. It's about 15 minutes. We'll do 2 more. Just so we can see all the different types you're going to run into. Find all the solutions of the equation on the interval 0 to 2 pi. Okay. So for this one, first I need to split it up into parts I can work with. Okay, because I ultimately want to solve for x with this. So I'm going to split this up. Sine of x times cosine of the second plus sine of the second times cosine of the first. Okay? I'm going to add to that sine of the first times cosine of the second minus, so minus, sine of the second times cosine of the first. Should equal, or does equal 1. You want to figure out when the x value gives you that. So then, I'm going to just go through and simplify a little bit. Cosine of pi over 2 is 0. So 0 times sine is gone. Sine of pi over 2 is going to be 1. So that's just going to be cosine. Cosine of 3 pi over 2 again is 0. So that whole term's gone. Sine of 3 pi over 2 is negative 1. So clean this up a little bit. What I actually have is 1 times cosine of x plus minus, and this is where you got to make sure you keep track of everything, minus a negative 1 times cosine. So that's going to be plus a positive cosine of x is equal to 1. Cosine of x plus cosine of x is 2 cosine of x. So then if I want to solve, I'm going to divide by 2. And then inverse cosine, or just pause and think for a second. On the unit circle, where is cosine of x? 1/2. Well, positive 1/2 is going to be in the first and the second quadrant. 1/2 of the distance away is going to be about here. Or I'm sorry, not first and second. I was thinking sine, first and fifth. And here. Well, that's going to be x is equal to pi over 3 and 5 pi over 3. That kind of question would be reasonable to have on a test. It's not, it looks really bad, but it really is not too bad once you get into it. This kind of problem is a little more complex when we on test, but it's a fun one to go through as far as those verification types go. Because you can't do verification with these sum and difference formulas. And the hard part here is to try to figure out which one's the more complex one. Because I would actually make the argument the one on the right is more complex, but I would actually do the one on the left because I can have those sum and difference properties that I can manipulate with. And I see x plus h here, so I'm going to split that up into pieces. When I do that, this top left is going to become cosine of x times cosine of h. That's plus, so since it's cosine we're doing minus. Sine of x times sine of h. That's still minus cosine of x. Now, I want to think about how I can manipulate this to turn it into this thing. Well, first off, I see the sines and the cosines are separated. So first thing I'm going to do is split those out. So I have cosine of x times cosine of h. I'm going to move the minus cosine over here, put all that over h, and then I'm going to move the minus sine x sine of h over h out to the right. Once you do that, it's not actually too bad to see, because they bring cosine of x out front. All they're doing is factoring that out. So they have cosine of x out front times cosine of h minus 1 over h minus, here they just pull out the sine of x times the sine of h over h. Those h's do not cancel off because they are, one's in a trig function, one is not. It's not too bad overall, but you gotta practice with it. You can't afford to honestly waste class time talking and messing around with stuff for this chapter, guys. I will be back on Monday. Please make use of the time.